I'm Victoria, and the name of our paper today is Neural-Symbolic VQA, Disentangling Reasoning from Vision and Language Understanding. So the first key to understanding this paper is understanding what the problem is that they're trying to solve. And that's visual question answering. And what does that mean? That means that the network is given an image, the visual component, and a natural language question, and it tries to parse that question and answer, or provide the correct answer with reference to the image. So for example here, what is the shape of the object closest to the large cylinder? So as a human, it's pretty easy to identify the tasks that we need to break this down into to answer the question. The first thing we do is we find the large cylinder here in the back. Then we find the object closest to it, and we observe its shape, which is a cube. Spacebar. Another example, this is from the Minecraft data set. So the question is, are there more trees than animals? So the tasks we need to do here are count the trees, count the animals, and then compare the two. This third example is a little bit more complex. How many blocks are on the right of the 3-level tower? It requires identifying a tower and identifying that a tower is made up of blocks, but ultimately what we need to do is find the 3-level tower here in the middle, look to the right, and count the blocks. And this final example here, this is a question that's a little bit more challenging for a network to answer. Will the block tower fall if the top block is removed? And this question is a little bit different from the others. It requires us to understand, first to find the top block, which is not the difficult part, but then to imagine removing it and apply our understanding of physics to actually decide whether or not the tower is going to fall down. So these are the kinds of questions that the network or the model that they've described in this paper tries to answer. So in order to do this, the authors have broken their model down into 3 large subtasks. So the first subtask is scene parsing. This is where the input image is turned into a symbolic representation. So this is accomplished with a convolutional neural network, and we input a color image, and then we output what looks like a table. The second task is question parsing, and this is the task of taking the natural language question and turning it into those tasks that we identified earlier to perform on the symbolic representation. And the third task is just to apply that parsed question to the scene representation and obtain our answer. So now that they've broken it down into these 3 tasks, there's a few advantages to breaking it down this way. The first is that they're able to greatly reduce the amount of annotated training data that's needed. This is important because, as we've seen in other papers, annotated training data can be really hard to come by. The second advantage is that both the scene representation, so the parsed scene, and then the reasoning module, which is that program executor, are both really lightweight, they're easy to compute, and they're easy to store. So just space concerns. And then the third advantage is that the reasoning process can be analyzed and diagnosed step by step. So in an end-to-end model, you have your input image, you run it through your network or series of networks, and you get your output at the end. And it's kind of a black box approach. So if you get the wrong answer, it's really hard to tell where your network is going wrong. So by breaking it down into these 3 separate modules, it's easy for the authors to diagnose which component of their model is actually causing the problem. So the architecture is broken down, as I mentioned, into these 3 components. The first is the scene parsing. So that's on the top row here. Again, your input is that 3 color channel image. And this is what your output looks like. So it's a visual representation of what your output is. So in this, each row is actually representative of an object. And then these are the attributes of the object that the network is able to identify. So a size, a shape, a material, a color, and then its 3-dimensional position. So next we parse the question. So we have our input here is the natural language question. And then our output is this series of commands in the language that was actually developed for use on this CLEVR data set. So filter shape would take the scene and filter out all of the cylinders, for example, and relate behind compares those x, y, and z coordinates. And then the last part is the most straightforward. It's just applying this program to this representation and coming up with your answer. So first we're going to focus on this top part, the scene parsing, and this is where the computer vision comes in. Oops, there we go. So the scene parser is actually two networks, or it's performed in two steps. The first step is a mask RCNN, which actually gives us the mask of each object. So it generates segment proposals. But while it's generating those segment proposals, another head on the network is actually generating the categorical labels. So mask RCNN is performing two functions. It's giving us these object masks, and it's giving us the categorical labels, which are size, shape, material, and color. So it's doing both the segmentation and the classification. And then all of the segment proposals with an object score of greater than 0.9 are passed on to the next step, which is the second half of the network here. Excuse me. So in the second half of the network, we have our object masks, and we have our original input image. So step one is to resize each object segment to 224 by 224 for uniformity. Next, we take that object segment, the resized object segment, and we pair it, excuse me, we pair it with the original input image. It's because what we're trying to do in this last step is figure out those x, y, and z coordinates. So in order for our network to be able to understand where that segment is, we need to pair it with the original input image. And the network that we pass it to is a ResNet 34. And then finally, we predict those continuous values. All right, so that covers the scene parsing from input image to symbolic representation. Step two is the question parsing, and this takes us from natural language question to program. So here's the figure a little bit bigger. So you can see we start with our natural language question. We output a sequence of commands, which is a sequence-to-sequence translation problem. So basically you have our input language, which is natural language, and our output language, which is the program language. And there's a really popular way to do this. LSTMs are frequently used for sequence-to-sequence translation. It's one of many options, but it's a popular one. And LSTM is a recurrent neural network, but it's a specific type that has a few extra logic gates that basically adjust for vanishing and exploding gradients. But that's a little outside the scope of this. So the encoder, we're using an encoder-decoder architecture. The encoder is a bidirectional LSTM. So a bidirectional LSTM is different from a traditional LSTM in that a traditional LSTM looks backwards at the previous input tokens while it's trying to predict the next output token. A bidirectional LSTM looks both backwards at the previous input tokens and ahead at the next input tokens. So our encoder embedding E sub I at time step I is given by both the forward and the backward output. The forward and the backward output embedding, where E sub I forward and H sub I forward are the encoder and the final hidden layer of the forward network. That's what the F is up here. That's derived by applying the LSTM to the embedder word encoding of the input token and the previous, or the hidden layer of the previous token. The backwards embedding is derived in much the same way, except for rather than looking at the hidden layer of the previous token, we're looking at the hidden layer of the next input token. So now we have our encoder embedding. For the decoder, we're using a straightforward LSTM. So the output of our decoder is Q sub t for time step t, and then the LSTM is applied to the decoder word embedding applied to the previous output token. So that's y sub t minus 1, and we'll look at how we get that y sub t. So once we have our encoder embedding and our decoder embedding, we're going to do a little bit more work with the decoder the decoder output. So we're going to take the decoder output and we're also going to combine it with an attention weight matrix and the encoder embedding and exponentiate that, and that's going to give us our attention matrix. The attention matrix is used to, along with the encoder embedding, is used to calculate the context. And then the context is paired with the output of the decoder, softmaxed, and that gives us finally our y sub t, where in the next step we're going to plug in here for the decoder. And our y sub t is going to be each of these output tokens. So each one of these is y sub 1, y sub 2, y sub 3. So now we have our representation, we have our program, and the last step is simply to apply the output of the question parser to the output of the scene parser and execute our program. So just to run through one more quick example to make sure we understand how that works. In this image is paired with the question, how many cubes that are behind the cylinder are large? So the first thing we want to do is we want to find, let's see, we start with finding the cylinder. So we're actually going to filter the shape for cylinders, and we're going to run this relationship and look behind the cylinder. So this output represents all of the objects that are behind the cylinder. The next thing we're going to do is filter the shape, which is cube, and then filter the size, so we're only going to have large cubes here left. And then finally, our last command is to count these rows, and so we get 3. So how many cubes are behind the large cylinder? Excuse me, how many cubes that are behind the cylinder are large? There's 1, 2, 3 large cubes. All right, so scene parser, question parser, program execution. Now, how do we train this model? We do it in steps, of course. So in the first step, the authors train the scene parser, which is those 2 CNNs. So the first CNN is actually trained on the CLEVR dataset, and they have ground truth object annotations or ground truth masks to train it on. So that's just a simple supervised training problem. Next, in the next step for the second CNN, the proposed object segments are paired with ground truth from the closest object segment in the original data set of their x, y, and z coordinates. So we have the proposed segments and the real x, y, and z coordinates. Those are paired together to train the second CNN, the ResNet34. And that one they call their attribute extractor because it extracts the continuous attributes. They run this for 30,000 iterations. They have 4,000 images to train on, and they do it in 8-image mini batches. So we have our scene parser trained. Next, we need to train the question parser. So the question parser training is unique. This is the one where the annotated examples are expensive to come by. So we use a small subset of those annotated question and program pairs. That's what we're calling our annotated examples. So the pairs of, say, like the natural language question and those step-by-step instructions. They use a small subset and do a fully supervised training. And then with the remainder of their questions, they perform reinforcement training. So in this case, the question parser is paired with the program executor, and the question is fed into the network, the program is run through the executor, and then the answer to the question, we have question and answer pairs in this part of training. The answer is used to generate a reward signal. And that reward signal is propagated backward through the network as the gradient on which to train. So that runs for a maximum of 2 million iterations, but they do implement early stopping. And then the program executor, of course, doesn't require any training. So let's take a look at some quantitative results. Along the top here, we have 5 different types of questions and then an overall score, which is the average of the 5. So in the CLEVR dataset, all of the questions are written according to a template and belong to one of 5 categories. So the count questions are the ones that ask how many. The exist questions are the one that ask, is there a sphere behind the cube? Compare number questions, of course, are there more than or are there less than? Compare attributes, ask if things are the same shape or the same color. And query attribute questions are asking what is the material or what is the color. So we have these 5 kinds of questions. And this is how humans perform on this task. So overall, we get about 92% of these questions right. You can see that some of them are worded a little bit confusingly, so it's not surprising that we don't get 100%. But let's compare that to some machine models. So here's a list of existing architectures for solving this problem at the time the paper was written. And pay special attention to this line here that says IEP. This is the architecture that was developed by the team that actually developed the CLEVR data set. So overall, IEP gets a score of almost 97%. So it does better, it outperforms humans on this task. There's a little bit of room for improvement. In fact, other people have already improved on this architecture. But let's see how NSVQA does. So we have 3 results here. The difference between them is the number of annotated training examples on the question parser. So either 90 question program pairs, 180 question program pairs, or 270, and then the remainder of the questions are used for that in that reinforcement training step. So when we use 270 annotated examples, NSVQA pretty much blows the rest of the architectures out of the water. And all of these are the reported mean of 3 runs. So I believe they reported the standard deviation of this last line here to be less than 0.1, so fairly confident numbers. Some more quantitative results. In this chart, we have along the x-axis the number of annotated training examples, or the number of programs that are provided to train the question parser. And we have 3 lines here that are the NSVQA, and that's how many question answer pairs, so the reinforcement pairs, were used to train it. And then we have IEP trained on both 7,000 and 9,000 question answer pairs. So you can see accuracy along the y-axis, NSVQA is outperforming it clearly. The second chart is actually measuring not the accuracy of the answer, but the accuracy of the outputted program. So when the question parser is actually run, maybe we're getting the right answer, maybe we're not, but is the program we've output correct? And it's comparing the number of annotated training examples in NSVQA in red here, and then IEP in blue. And you can see, again, NSVQA just vastly outperforming the competition. And then finally, this is the total number of training questions used along the x-axis and the accuracy along the y-axis. NSVQA in the blue line at top is, again, leaps and bounds ahead of the others. When you get up to 700,000 training questions, they all tend to get pretty high accuracy, but below that, it's really important that with the fewer training questions, NSVQA is the clear leader. So let's look at some qualitative results and see how this network is actually doing what it's doing. In this first example here, we have the question, what number of cylinders are gray objects or tiny brown matte objects? So we're comparing in this example the output of the NSVQA and the IEP, and let's look at their programs. So NSVQA, blue is correct and red is incorrect. So until the very last step, IEP is making incorrect, or is outputting incorrect steps. It does get those last few correct though, but ultimately outputs the wrong answer. Meanwhile, NSVQA outputs the correct program and gets the correct answer. So the second example demonstrates something that the authors, in comparing the results, saw kind of frequently. For this image, are there more yellow matte things that are right of the gray ball than cyan metallic objects? So it's a very roundabout question. The program is longer than they printed here, but they do get the right answer and their correct program. But the IEP model gets the correct answer, but outputs the incorrect program, and it's very long actually. They have 25 modules in here. So sometimes in measuring the accuracy, IEP is actually getting the correct answer but going about it incorrectly. So the next question the authors wanted to answer is, can this architecture generalize to new combinations of attributes? So to do that, we have two sets of data. We have condition A, which was used for training. And condition A contains cubes of only these colors and cylinders of only these colors, which are mutually exclusive sets of colors. And then they have spheres of any colors. So the idea is to limit the combinations of attributes. And then for evaluation, of course, we invert the classes of colors so that the cubes are now in colors that have not been seen on cubes before, and the cylinders are in colors that have not been seen on cylinders before. But all of these colors were in the training data. All of these shapes were in the training data, just in different combinations. All right, so for results, first we have all of these networks were trained on set A first. And then in this first column we have the results of these networks on set A. So if we're trained on set A and we evaluate on set A, our performance should be pretty good. If we train on set A and evaluate on set B, you can see the performance takes a hit. So say we only have a few, or say we train on set A and we want to maybe fine-tune on set B. So now, once we fine-tuned on set B, the same trained on A, fine-tuned on set B, now these are our results on A, which have taken a hit, but our results on set B have improved. So these are existing architectures. Again, IEP is the one that the authors use in a few other comparisons, so there's the line to pay attention to. Now here's the NSVQA results. So again, in this first line we have trained on set A, tested on set A, performs great. Trained on set A, tested on set B. It performs poorly except for this last model here, which we'll talk about in a second. And then if we actually go in and fine-tune our model, when we train on set A and fine-tune on both A and B, we get the best results here on both set A and set B of any of the architectures. So these last two lines here, the authors ran a couple of additional experiments. In the plus gray example, they added a gray channel to the scene parser to see if that gave some generalization about the colors. And then in the plus ORI, they actually just used the original scene parser that was trained on the full original data set. And that one actually does outperform all of the others. So even if our question parser has not learned those things before, just having the scene parser trained on both of those original sets, then that improves our performance. All right, so here's the really challenging questions. This data set is called CLEVR-Humans, and it's clever images paired with human-generated questions from Mechanical Turk. And these are free-form questions, so they can be a lot more challenging for the machine to answer. For example, what shape is the object reflected in the blue cylinder? And reflected in was not part of the original template, so this one is going to be hard for our network to comprehend. And then on the right we have what number of cylinders share the same color. So share the same color again is something that our network should be able to do, but it's worded in a different way, so it's going to be a challenge for it to recognize and get the correct program. So how does it do? It does worse than the CLEVR data set, of course, but it actually outperforms IEP by a pretty large margin. So we're moving forward and improving on the previous results here. And actually answering about 67 is almost 70%, about 2/3 of the questions is actually pretty impressive. And then finally, they wanted to apply their architecture to an entirely new problem. So they used scenes from Minecraft. And these were all generated from a Minecraft scene generator, and they were able to choose 12 entities that they wanted to include in their screenshots. And each of the screenshots contains 3 to 6 of these entities. So the attributes that they're looking for are a category, 2-dimensional coordinates, and then the direction that the entity is facing. And the category is actually hierarchical, so that's an additional layer of challenge here. For example, the network has to be able to identify both a wolf and a pig, but it also has to identify both wolf and pig as animals. So, here's an example of a Minecraft screenshot. How many trees behind the farthest animal? Well, there's our farthest animal and there's our one tree. So we can see that NSVQA actually does output the correct program and the correct answer. What direction is the closest creature facing? So it actually identifies this occluded creature here, identifies it as, or partially occluded, and then identifies it as the closest and gets the correct answer. So pretty impressive results. Not quite as great as the CLEVR dataset, which was designed specifically for this problem, but still impressive. Unfortunately, we didn't have anything to compare it to because they generated this data. So, in summary, their architecture does successfully disentangle the visual perception from the logical reasoning by training or by modeling and training separately. And then their two-step process of doing the supervised training with the annotated examples and then the reinforcement training with the question-answer pairs greatly reduces the number of annotated or question program pairs that we need, and those are the expensive ones. So that's also a success. And then as we can see from the additional experiments, the architecture and the training process is pretty generalizable to the new contexts. The only downfall is that in order to answer a question, you have to actually build that program executor model. So that's where I think that there's a little bit of room for improvement on the model. And that is it.